Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the equation of free vertex flow. So in our previous lectures already we have discussed the concept of vertex flow and the concept of force vertex flow, and also we have discussed the concept of free vertex flow also. But in this lecture we will discuss the equation of free vertex flow. And before going to discuss this equation, let me remind you that what we have discussed regarding our theory part of free vertex flow, and also I have told you the equation of this free vertex flow. So if you remember that one, that during this free vertex flow, what I told, like I have considered a fluid particles of mass m, and at a radial distance of suppose r it is present, and from the axis of rotation, suppose this is the axis of rotation, this is the fluid particle, okay, and suppose this is a sink basin and the water is coming from here, okay, and there some vertex formations happen, and this is happened by naturally or freely. So that mass of the fluid element, let's consider m, and that is situated with a distance of r, and the axis of rotation having a tangential velocity v. So we can write, we can write the angular velocity, or we can say tangential velocity is, this is taken. So next we can calculate angular velocity, omega will be there, and now we can find out the angular momentum. We can write the angular momentum equal to, here we can write the mass into velocity. These things already I have told you previous during free vertex flow. Let me remind you again this same thing, angular momentum equal to mass into velocity. And next I can calculate the moment of angular momentum, the moment of angular momentum. This we can write, the momentum, angular momentum into the radius which is present here. So that one we can write m into v into r, m equal to mb, small mb, and this is the radius mb here. So now if you want to write the time rate of change of momentum, okay, the time rate of, okay, change of angular momentum, that we can write derivative of, derivative of these things with respect to time. So derivative of what? A derivative of mvr with respect to time. Okay. So now we can say that for free vertex flow, we can write this del t into mvr equal to 0. Okay. And now integrating this equation from both sides, what will get? Integration of this one. So again we can write mvr equal to, will get constant. Integration of this 0 part, let's consider is the constant. Now what will get here? We can write vr equal to constant by mass. So constant by mass, we can write same thing again, it is a constant. So what we got here, the vr equal to, we got a constant here. So this equation already we have discussed regarding the free vertex flow. Now same equation we will consider here to derive the free vertex flow. Okay. Now for these things we will start from here only. So what I'll write here, same thing I can write like v into r equal to constant c, and if I want to write v equal to, I can write c by r. These things I can write. Now what I'll do, in the previous, again I got a derivation of vertex flow only, general equation for the vertex flow. That equation, actually let me write this equation, that we got pressure variation equation del dp equal to rho v square by r into dr minus rho g dz. This is the pressure variation equation for the, or you can say the generalized equation for the vertex flow, whether it may be in horizontally or it may be in the vertically. Of this part we have discussed regarding the horizontal condition, when it is moving in the horizontal plane, and this is while it is in the vertical one, because dz is there. okay, Z, and this is R is there. Okay, so this came from the hydrostatic law, and this one our vortex flow, which is flowing when when the liquid is rotating in a horizontal plane. Okay, so this equation already you have derived in the previous videos. You can see that one also. Now what I'll do here, I'll put this value of V in this equation. So what will be there here? I can write dP equal to rho into V square by R. Now what I'll do, the same, I'll put this value of C by R on this. So C square by, here already V square value C by R, that means C square by R square, C square by R square into R. So I'll get here R cube, okay, into dr minus rho g dz. This is the equation. Now again I can write C square by dP equal to rho C square by R cube dr minus rho g into dz. Okay, this is okay. Now this equation we got after implementing the value of V velocity in this generalized equation. Now let consider 2 points here. What are the 2 points? Because this is the diagram what we have considered for the free vortex flow, and here when the liquid is flowing downward, okay, when the liquid is flowing downward, you can see this forms a vortex form, we know that's one, and this is the central line or axis line of this you can consider. Now let's consider some points on this liquid. Let's consider 1 point and second point. 2 points 1 and 2 of fluid having radius of, suppose first point is there 1, and that is located with a distance of r1 from the axis, central axis line. Okay, and the second point which is located with a distance of r2 from the central axis line, okay, which is perpendicularly downward. Okay, so the distance from this, from this base, if you consider the distance of this r1 and r2 is given z1 and z2 distance. This is z2 distance and this is z1 distance. Okay, and now we can integrate this equation what we got here, integrate this equation by considering this point. Why I have shown this point? By considering these points we are going to integrate this equation. Okay, so if you integrate this one, let me write dP integration 1 to 2. Okay, similarly integration of 1 to 2 rho C square by R cube into, we can write dr minus again integration 1 to 2 rho g and dz. So this is the equation. Now we'll start the integration part. Okay, now integration of this dP will get p. So p, upper limit, lower limit, that is 1 and 2. So you can write p2 minus p1. Okay, next we'll get here rho c square, let's take it outside, is a constant, and integration of 1 to 2, and this will be, remaining part will be 1 by r cube, because r is there, dr is there. So what I'll write, let write r to the power minus 3. This r cube I have taken to numerator, and r to the power minus 3 into dr minus integration of 1 to 2. So here also I'll do one thing, rho g I'll take it outside, and in the integration part I'll keep only dz. Okay, now this p1, p2 minus p1, let it keep it as usual, and this one let's solve this one. So rho, so this is c square and r to the power minus 3, and so if you integrate this one, like integrate one limit 1 to 2, will get minus 2 bottom, like in the denominator, and here we will get r to the power minus 2 and r to the power minus 2, and this like upper limit, lower limit will be there 1 to 2, and similarly here rho g, and similarly this one z will get dz, will get z, and that is also 1 to 2. So this is the equation what we are going to get. Now after that, one more line let me write here. Again I can write rho c square by minus 2. This is only integration and derivative we need to do it here, and here we'll put the upper limit and lower limit value. So what we'll get here? R to the power minus 2. So this one we can write in bracket R2 minus 2, and this is R1 minus 2. So here again we can write rho g in bracket Z2 minus Z1. Okay, so this is the equation what we are going to get from that. Again we can solve it. Let me write another page. So here let me start from the starting. P2 minus P1, and this equal to, we can write minus rho c square by 2, and here we can write this, what we written here, R2 minus to the power minus 2 and R1 to the power minus 2. This one we can write 1 by R2. So what I'll write here, I'll write 1 by R2 square, and this is 1 by R1 square, bracket close, and we can write rho g into Z2 minus Z1. That is as usual, we can keep it. Okay, again same thing we can write here. This is 1 by R2. Okay, now what I'll do, C I'll keep it inside. Okay, so again minus rho by 2, and here c square by R2 square. In the previous step also I can do this, c square by R square, and one more step if you want to write, we can write also c square, this is R1 by R1 square minus rho g into Z2 minus Z1. Now if you see this value, c square by R2 square, c by R, let me show you here. Yeah, if you see this value, V equal to c by R. So what we'll do here, we'll just put the value of c by R on V. That means on behalf of this value, we'll put the value of V. So what we'll get here, minus rho by 2, here we'll get c by 2, means that means we can write V2 square. V2 square, this is, we can write V1 square minus rho g into Z2 minus Z1. Okay, and similarly we can write, okay, this minus term we can take it to inside. So after taking inside, what we can write here, now rho by 2, and here we'll get V1 square minus V2 square into rho g Z2 minus Z1. Okay, this is our P2 minus P1. This is the value. Now here what we'll do, we'll divide rho g. Okay, we'll divide rho g in all these sides. Let's divide rho g, all sides. So what we're going to get here, now P2 minus P1 by rho g equal to, if you rho g divide here, rho will be cancelled. So what we'll get here, V1 square minus V2 square divided by 2g, and here rho g will be cancelled. So only like Z2 minus Z1. So if you look this equation, and if you elaborate this equation again, what we are going to get, P2 minus P1. So again we can write this is P2 by rho g minus P1 by rho g. Okay, so again let me write this. This one we can elaborate, means we will get in this way. Okay, let me write in this way, P1 by rho g plus V1 square by 2g plus Z1. If we elaborate this one, we'll get the value. Okay, and also you can write this P2 by, similarly, rho g plus V2 square by 2g plus Z2. Okay, this is equation we are going to get from here, and this equation is actually known as the Bernoulli's equation. Okay, if you know the Bernoulli's equation, then this is the part of Bernoulli's equation. So that means what it defines here. So this Bernoulli's equation, okay, this equation, Bernoulli's equation, actually, in the case of free vertex flow, this Bernoulli's equation is applicable. So from here, what we are going to learn, that means for the free vertex flow, Bernoulli's equation is applicable. Okay. So these things very simple only. You'll keep P2 by rho g. If you extend this one, very simple, we can keep it, P2 by rho g minus P1 by rho g, and this is V1 square by 2g, and this is minus V2 square by 2g, and this is minus Z2, and this is plus Z1. So keep, this P1, you take it to this side, suppose. So here plus minus will be there, it will be plus. So this is V1 square, P1, Z1. All it came plus, okay? And this is P2, already plus is there. Now V2 square, take it to this side, then it will be plus. Again, Z2, you take it to other side, then that will be also plus. The same thing I written directly here. Okay, so here what we have learned, that means for the free vertex flow, the Bernoulli's equation will be applicable, and this is the equation of free vertex flow. So I hope you understand what is this free vertex flow equation. If you are having any doubt regarding this, you can give a comment on the comment box. Thank you all.